Okay, this video is about another common use for the chi-square distribution called contingency tables. The setup may look a bit like two-way ANOVA because of the rows and columns, but there's no response variable to worry about. We simply cross-reference each member of our random sample and tally up the total number of observations that fall into each combination of categories. This actually has more in common with one-way ANOVA than two-way ANOVA. The chi-square formula is the same as last video. It's observed minus expected squared over expected. The double sum means that we'll be adding up across all rows and columns. And this results in a chi-square distribution with r minus 1 times c minus 1 degrees of freedom. Just remember that r is the number of rows and c is the number of columns. Our first example is about brand loyalty and cars. We asked 500 new car buyers what their last car was and whether or not they intend to buy the same brand of car. Here are the results. These are the observed values that we'll use later in the formula. In order to calculate expected values, we need row and column totals. Here are the row totals, and here are the column totals. Notice the row totals are denoted by R, and column totals are denoted by C. And lastly, our sample size of 500 is still called N. The formula for expected value is a bit different than the last video. Each combination of categories has its own expected value. The little ij in the corner refers to its row and column in the table. So the expected value of row I, column j is that row's total times that column's total divided by n. Here are all of the calculations. Notice how the row and column totals keep changing to reflect the position in the table. However, we always end up dividing by 500, the sample size. The calculations turn out like this, and these are the expected values we'll be plugging into the chi-squared formula. So let's get to the formula. There are 6 combinations of car brand and customer loyalty, and each has its own observed and expected value. So there are 6 terms in the sum. Here are the terms from the first row of the table, and here are the terms from the second row. And it all adds up to 17.27 with 1 times 2 degrees of freedom. I'm not going to draw a picture of the chi-square distribution with 2 degrees of freedom since it was in the previous video. And at 5% level, the critical value is 5.99. And since 17.27 is greater than this, we would reject the null hypothesis. But I haven't even told you what that hypothesis is yet. We'll get into that next. Part of the reason why I didn't start with the hypothesis like usual is because there are several different ways to express it. First, we can express it in terms of row distributions, and I'll talk very soon about what row distributions are. But for now, let's define the null hypothesis as row distributions are equal, and a rejection would mean that they are not equal. Second, we can phrase it in terms of column distributions. The null hypothesis is that column distributions are equal, and a rejection would mean that they are not equal. Third, we can phrase it in terms of independence. The null hypothesis is that the 2 variables are independent, and a rejection would mean that they are dependent. I'm talking about independence in the same sense that you learned about in IntroStat. Let's begin with row distributions. We're going to divide each row by its total to make percentages. That's all a row distribution really is. Let's start with the first row. Its total is 190, so we'll divide each number by 190 to get these percentages. And these all add up to 100%. The total for the second row is 310, so we'll divide that row by 310 to get these percentages. Again, it adds up to 100%. These are the row distributions. The first row distribution represents the distribution of car brands among loyal customers. And the second row represents the distribution of car brands among disloyal customers. Just looking at the numbers in the two rows, we can tell they are not at all similar. So it should not be a surprise that we rejected the null hypothesis that they are all equal. Speaking of the null hypothesis, let me show you what the data would look like if the null hypothesis were true. To do that, we need the distribution of the column totals. We find that by dividing them by the sample size 500 to get these percentages. If the null hypothesis were true, then both row distributions would be equal and look like this. Next, we'll look at column distributions. The idea is very similar to row distributions, except now that we'll be dividing by column totals. There are a total of 140 Ford customers, and after we divide by the total, we get these percentages, and they add up to 100%. There are 180 Honda customers, and after we divide by that total, we get these percents. And we can do the same thing for Chevy customers. These are the column distributions. The first column represents the distribution of brand loyalty for Ford. The second column represents the distribution of brand loyalty for Honda. And the third column represents the distribution of brand loyalty for Chevy. Looking at the numbers, we can see that Ford and Chevy are pretty similar, but Honda is very different. So it should be no surprise that we rejected the null hypothesis that they are all equal. And let's see what the data would look like if the null hypothesis were true. We need to find the distribution of the row totals by dividing by the sample size 500. If the null hypothesis were true, then all of the column distributions would be equal, and they would all look like this. Next, we'll look at the idea of independence. We'll begin by finding the joint distribution of the two variables. The joint distribution is relatively simple to do. We just need to divide every number by the sample size, 500. That gives us these percentages. This is the joint distribution of car brand and customer loyalty. And all of these numbers must add up to 100%. An experienced statistician might be able to glance at these numbers and tell that they are not independent, but let's see how it works. Let's see what the data would look like if they really were independent. And I need you to think back to the introstat definition of independent events. Independence meant that individual probabilities could be multiplied together in order to find the probability of that combination. So using independence, let's find the probability of getting a loyal Ford customer. It would be the probability of being loyal, 190 over 500, times the probability of being a Ford customer, 140 over 500, or 10.6%. And we can continue like this through the rest of the table. As a side note, do you see the similarity with the expected value calculation from earlier and this calculation? Anyway, this table shows what the data would look like if it was totally independent. And if you rewind to the joint distribution in the previous slide and compare it to this table, then you'll see that they are rather different. After all, we did reject the null hypothesis that they are independent. With 3 different ways to express the null hypothesis, we have 3 ways to express the results. All 3 of them are mathematically equivalent. You just need to consider your audience and try to pick the one that helps them to best understand the results. Remember that our chi-squared test resulted in a rejection, so here's how you explain that in plain English in 3 different ways. If you decide to use row distributions, then you could say something like, the car brand distributions of loyal customers is not the same as the car brand distribution of disloyal customers. If you decide to use column distributions, then you could say something like, the proportions of loyal customers are not all equal between Ford, Honda, and Chevy customers. And finally, if you decide to use independence, then you could say something like, customer loyalty depends on car brand, or vice versa. Car brand depends on customer loyalty. Choose whichever one makes the most sense. In this particular problem, it makes sense to me to assume that car brand has an effect on customer loyalty and not the other way around. So column distributions, they make the most sense to me. But that's simply my opinion, and there's no other way to distinguish between these options. All right, this example is about voter preference in the 2000 US presidential race between Al Gore and George W. Bush. The 2 variables are education level and presidential vote. Go ahead and copy this data down since you'll need it to answer the 3 questions coming up. Good luck with that, and I'll see you in class.